So I was asked to give the second talk on H1 in the universe, and I thought that was kind of to do it that way would be to uh, cover many things in kind of a piecemeal fashion, with spending a bit, spending almost no time at all on each of those things. And so I decided instead, especially since uh, we lost Govind Swarup just about a few months ago, it would be probably appropriate to do a tribute talk to Govind and kind of link up with the building of the GMRT. So what I decided to do was to give you a talk on H1 21 centimeter emission studies of galaxies, of gas and galaxies, focusing especially on the high redshift universe. And I'll basically take you from the early days of 21 centimeter studies all the way up to 2020. And I should acknowledge Aditya Chaudhary, who basically did or led the work that I'll talk about right at the end of this talk, and who also was responsible for, who also made one of the movies that you'll see in the talk later. So that's the broad background for this talk. I'm going to tell you about H1 21 centimeter emission studies of galaxies and why we do them and what we hope to get from them in the future. And of course, a lot of this, certainly the recent stuff, will be based on work with the GMRT, which is the telescope that you see in the background from the Narayangarh Hill. So this is a broad outline of the talk. I'm basically going to do what's the word? A history of 21 centimeter emission. And so we'll start with the 1940s actually, but the 1950s was when the 21 centimeter line was first discovered in the universe, in astronomical objects. And I'll skate through the 60s. The 60s had lots of interesting stuff, especially if you're at Berkeley and Paris and so on, but skate through the 60s. And we'll jump straight to the 70s, where suddenly issues came up about the content of galaxies, what kind of matter was present in galaxies. Then I'll move to the 80s, where things started to change, and we started to understand a little bit more about the content of matter in galaxies. And that was also the time when the GMRT was, if you like, started to be born. I think that's the right word. The plans were made for the birth of the GMRT. And in the 90s, we moved on to the death, if you like, the demise of one of the popular models of dark matter, the universe, the hot dark matter model, which, as you will see, was the reason for building the GMRT. The GMRT came online in 2002 and has done a whole bunch of work in the last 20 years. And then around the same time that the GMRT came online or was being built in the 90s and early 2000s, stars started to dominate, if you like, our understanding of the universe, and especially the high redshift universe. So I'll take you through that and take you through some of the questions that have arisen as a result of lots of optical and near-infrared studies of high redshift galaxies in the stellar emission. And then finally, I'll move to at the end of the talk, I'll tell you about how we have finally started to use neutral hydrogen 21 centimeter emission to probe gas in these high redshift galaxies, and what we hope to do over the next, let's say, 5 years or so. That's the broad outline of the talk. So this is something that I thought I'll just rehash this a bit. I said that in hydrogen and hydrogenic atoms, you have the standard transitions that electrons make from principal quantum number energy levels, n equal to 1, 2, 3, so on, and which give rise to, in hydrogen, the Lyman-Balmer-Paschen series, depending on the lowest state of the transition. So the Lyman series, for example, is transitions to the ground state of neutral hydrogen, n equal to 1 state. The Balmer series is transitions to n equal to 2. And all these transitions from higher energy states are accompanied by the emission of a photon of a well-defined wavelength or frequency. The important thing, though, is that these transitions are very strong transitions, and the strength of a line is defined or is quantified by means of what is called its Einstein A coefficient, which is the probability of spontaneous emission of that line. So for transitions in the optical, such as the Lyman-Balmer-Paschen series, the Einstein A coefficient is about 10 to the 8 per second. So particles stay in the upper states for a very small amount of time, and they shoot down to the ground state. And that's a picture that you should have for all these electronic transitions. They're very, very high probability transitions. And these arise at ultraviolet or optical wavelengths. Now, the exact opposite is the case for the 21 centimeter line. This is not a transition between principal quantum number energy levels. In fact, this is an example of a genuine quantum mechanical transition because spin is not a quantity that exists in classical mechanics in the atom at least. You can kind of sort out the Lyman-Balmer so on things with a semi-classical approach to quantum mechanics. That's what Bohr did. But you can't account for spin in such a semi-classical approach. And the 21 centimeter line arises because in the ground state of atomic hydrogen, neutral hydrogen, there are two possible orientations of the electron spin relative to the proton spin. And the state in which the electron proton spins are parallel, the one which is in the top left over here, has a slightly higher energy than the state in which they're anti-parallel. And so you can make a transition from the parallel spin state to the anti-parallel spin state with the emission of a photon at a frequency of about 1420.40575 megahertz or lambda of 21.11 centimeters. And this transition has been immortalized as the 21 centimeter line. This line, unfortunately, sadly, truly sadly, is terrifyingly weak. It's got an Einstein A coefficient of 10 to the minus 15 per second. And I'll say that again, it's 10 to the minus 15. It's 23 orders of magnitude smaller than, for example, Lyman alpha's Einstein A coefficient. So it's ludicrously, ridiculously weak, right? But yet, it is probably the most important line in astronomy. And it's just because, despite the fact that, maybe because the line is weak, it turns out that instead of all the particles being in the ground state, being in the anti-parallel spin state, you wind up with the particles being distributed in the upper and lower states by roughly the statistical weights of the states. So there are roughly 3 particles in the upper state and 1 particle in the lower state for every 4 particles in the universe. And that turns out to have very interesting consequences. I won't really go into that in this talk, but the fact that the Einstein A coefficient is so low, making the line weak and hard to detect, actually has good implications for us. So anyways, in the middle of World War II, Jan Oort, who was a spectacular Dutch astronomer, had just come across Grote Reber's studies of continuum radiation, especially both from the sun and from objects inside the Milky Way. Grote Reber was the first, if you like, radio astronomer. He was probably the only radio astronomer for about 8 years. Karl Jansky has some claims to be the first radio astronomer, but I would probably think of him more as a radio engineer than a radio astronomer. But Grote Reber, for about 8 or 9 years, was the only radio astronomer in the world, from 36 to about 44. Anyway, so Jan Oort suggested to a bunch of students that it would be nice to check if you can find spectral lines in the radio. And the reason for that was exactly what I said 2 days ago, that Jan Oort realized that radio signals would not be affected by dust. And so they could be used to probe, for example, the structure of the Milky Way. And a smart grad student, Hendrik van der Hulst, in 1944, while the Germans were in the occupied Netherlands, van der Hulst argued that the atomic hydrogen 21 centimeter line should be detectable or could be detectable in astronomical circumstances. And so after the war, Oort and a few other people, Oort especially, led a group which was trying to search for the line. And Doc Ewen and Ed Purcell in the US, and also Chris Christensen in Australia, led similar searches for the 21 centimeter signal. And each of these groups independently detected the line, Ewen and Purcell marginally before Muller and Oort, and Christensen and company slightly later. And so there was a series of papers on the first detection of 21 centimeter emission from objects in the Milky Way. And this was the first spectral line in radio astronomy. And people jumped up and down about this. It was fantastic. Oort promptly went off and started mapping the Milky Way with this line and came up with the structure of the Milky Way, if you like. And then in 1954, Kerr and company used Christensen's dish to detect 21 centimeter emission to the Large Magellanic Cloud. And that was the first detection of a radio line from an external object outside the Milky Way. And that opened up a whole new field. You could suddenly now do all kinds of stuff you could probe external galaxies using this 21 centimeter line. So what do you get from the 21 centimeter line? So galaxies are basically made up of stars and gas. The baryons in galaxies are stars and gas, and about 75% of the gas is hydrogen, of everything is hydrogen by mass. And galaxies are not closed box systems. Galaxies are extremely complicated systems. But if you want to think of a galaxy, you can think of a galaxy as something into which there are flows of ionized gas from the circumgalactic medium or the intergalactic medium. And this gas cools and settles into a disk and forms atomic hydrogen. This disk further cools, usually via metal line radiation, and forms molecular gas. The molecular gas then self gravitates, collapses out, and forms stars. The stars live happy lives, sometimes with astronomers on nearby planets. And at some point of time, the more massive ones go boom, and they produce supernovae. And these supernovae chuck metals into the interstellar medium, and the metals mix with the atomic gas and cause further cooling. And this cooling causes gas to become colder, almost by definition, causes the formation of molecular gas, which again leads to stars, leads to supernovae, leads to metals, leads to gas, in this beautiful cycle, which is basically a galaxy. And some of the metals, because of the supernovae drive winds which blow the metals and some of the gas out of galaxies, and this can actually cause star formation to stop. But that's the general picture of a galaxy's life cycle. The thing to take in from all of this is that atomic hydrogen, H1, is the primary fuel for star formation in the universe. So if you want to understand star formation in galaxies, you have to look at both the stars and the fuel for the star formation, which is the H1. And it turns out that the 21 centimeter emission line strength is proportional directly to the atomic hydrogen gas mass, to the H1 mass. And this, it turns out, is the only way that we know of to measure the atomic hydrogen mass of galaxies. So if you want to measure the fuel for star formation directly, you've got to use the 21 centimeter emission line. Sadly, as I said a little while ago, the 21 centimeter line is weak, and that makes it really hard to detect at cosmological distances, just because the Einstein A coefficient is so low. But that didn't stop the folk in the 50s and 60s. They weren't worried about cosmology. They just went off and used the telescopes that they had and observed as many galaxies as they could in the nearby universe and in the Milky Way. And so in the 60s, a lot of work was done on this, with usually with single-dish telescopes. In the 60s, also, Barry Clark discovered that H1 in galaxies can be both hot and cold, warm and cold as it's called. Temperatures about 100 Kelvin and about 6,000 Kelvin, two phases basically. And he discovered this, he realized this because he saw that the emission lines, which are not sensitive to temperature, are much wider than the absorption lines, which are sensitive to temperature. And so great, you had this picture by the end of the 60s that H1 in galaxies is both cold and warm. The cold gas, of course, is what actually further cools and becomes molecular hydrogen. And the warm gas kind of forms probably as the envelope of the cold gas clouds. And that was the picture at the end of the 60s. By the early 70s, things started to get interesting. Things started to get interesting because of spectral lines, not just 21 centimeter, but because of the nature of spectral lines. The fact that spectral lines provide velocity information. And so now if you have a galaxy, and if you have a galaxy which is rotating, the side of the galaxy which is moving towards you will produce blue shifted spectral lines, if you can observe them, if you can get a spectrum across the galaxy. And the gas which is moving away from you will produce redshifted spectral lines. And this is a picture that I showed you 2 days ago of an H1 21 centimeter map of the galaxy M33, which is a beautiful disk galaxy. There you can see in the left side, it's blue. The left side is moving towards us. The right side is red. The right side is moving away from us. And the velocity scale is relative to the systemic velocity, which means that the velocity scale is in the rest frame of the galaxy. So the center is at basically zero velocity. Now, this is interesting because if you can actually now measure the velocity as a function of the location in the galaxy, what you can do is that you can measure how the rotation speed of a galaxy changes with radius, how the velocity of a galaxy changes as you go further and further away from the center of the galaxy. And this is called the rotation curve of a galaxy. And you can see immediately that for gas and circular orbits around the center of a galaxy, the velocity, the rotation velocity, will basically be gm by r raised to half. And that's the usual, I'm sure all of you are familiar with this. And so what does this mean? If you look at the visible mass of galaxies, the stellar mass, the visible mass is mostly in the central regions of galaxies. The gas is basically right in the middle of galaxies. And you saw that a little while ago in NGC 6946, where you can see the stars are right in the middle of the galaxy. The H1 is, spread way out. And so if the visible mass is mostly in the central region, and if you take gas at the edge of the central region, outside the central region, then the mass is constant in that equation up there. So what you expect is that the velocity, the rotation speed, should be proportional to 1 upon r raised to half as you go to larger and larger radii. So it should decline with distance from the center of the galaxy. Your rotation curve, you would expect that the rotation curve might increase as you go out from the center initially, as more and more mass gets built up. And then as you kind of go beyond the point where you're picking up much mass, it'll start to decline. And then at very large distances, where the amount of mass, extra mass being added is very small, it should go like 1 upon r to the half. And that's the picture that you expect if most of your gas is baryonic. And what Vera Rubin found with optical H alpha spectroscopy in the early 70s, and then even more interesting, Albert Bosma found with the Westerbork synthesis radio telescope, the first of what I would call the great interferometers. What Vera and Albert Bosma found was that galaxies actually do not have declining rotation curves at large r. So what you see in the second figure over here is a plot of the velocity versus radius in units of 1000 light years over here. And the yellow points over here, so this is a plot, this is an image of the galaxy. The yellow points over here are from starlight. And the white points over here are from 21 centimeter emission. And the dashed curve that you see is what you expect, is the rotation curve that you expect from the visible disk. So you expect that the rotation curve will rise, go kind of flat, and then decline steadily like 1 upon r to the half, because all the matter is basically inside in this region. But what you actually see is that the rotation curve rises, and actually, for this galaxy, it keeps rising linearly almost at large radii. And what this is telling you, the only way you can do this is if the mass in this equation is somehow continuing to increase as you go to larger radii. The radius is increasing, of course, as you go to large radii. So the only way the velocity can keep growing is if the mass also keeps growing. And what you see in most galaxies is that it doesn't rise, but it stays flat. This is just a nice example, a nice figure which shows the optical in 21 centimeter, and it shows the importance of 21 centimeter. You really need to go far out of the galaxy to see this, continual rise or flattening of the rotation curve. From the optical, you can just go this distance, and you might say that, okay, beyond this point, it starts to decline, and that's it. And so by the end of the 70s, as you can see in this annual reviews article by Sandy Faber and Ken Gallagher, people were fairly clear that there must be invisible matter in the universe that was not simply stars and gas. And Faber and Gallagher said that it's our opinion that the case for invisible matter in the universe is very strong and getting stronger. So what matter is this? What is this invisible matter? And remember, this matter has to dominate the mass of galaxies. If you have to keep the rotation curves rising over here at very large radii, there has to be much more of this kind of invisible matter than there is of stars and gas. And so this was very, very, very perplexing. Anyway, the two kinds of matter that people were thinking about in the 70s and early 80s were relativistic dark matter, which is called hot dark matter. The particles are relativistic, or non-relativistic dark matter, which is, unsurprisingly called cold dark matter. And there were a whole bunch of articles in the late 70s and early 80s talking about the charms of these two paradigms of dark matter. And in the early 1980s, hot dark matter was a much preferred model. One reason for this was just the fact that there was actually a candidate hot dark matter particle, essentially a massive neutrino. Neutrinos are relativistic particles, and it was, people thought that if neutrinos have mass, they're the ideal particle for to explain hot dark matter. While cold dark matter, then and even today, does not have a carrier as yet. We don't know what the particle is for cold dark matter. And to make matters even better, hot dark matter models, at least in the early 80s, appeared to match observations of galaxies better than cold dark matter models. So wonderful, hot dark matter is a good candidate. Neutrinos are the particle that carry, that are the source of hot dark matter, and we move on. But the interesting thing was that the two models, hot dark matter and cold dark matter, had dramatically different predictions for the nature of galaxies, for how galaxies build up with redshift. What hot dark matter said was that galaxies at high redshifts about 3 and higher, are supermassive. And then these galaxies break up and form smaller galaxies at lower redshift. So you build the biggest galaxies first, and then you break them up to form small galaxies. And in such big galaxies, from such big galaxies, you would have extremely bright 21 centimeter signals from atomic hydrogen gas. Yakov Zeldovich was the person who I would say dominated the field for hot dark matter for more than a decade. Cold dark matter, on the other hand, was the exact opposite. In cold dark matter, you build up galaxies by mergers of smaller galaxies, and you expect to have far smaller galaxies at high redshifts, redshifts larger than 3. And then you build up galaxies as time goes on, and you and so small galaxies, you expect much weaker 21 centimeter signals because there's just much, much less mass in these galaxies. And so that gave you a clear prediction that hot dark matter should give you these really large galaxies with super bright 21 centimeter signals. Cold dark matter should give you basically no 21 centimeter signals. And in the early 80s, hot dark matter was the flavor of the month, so to speak, or the decade. And so it seemed like this was a clean prediction which would separate these models. And the redshift to 21 centimeter line frequency for redshifts of, let's say, 3, of course, is 1420.4058 divided by 1 plus z. If you put z equal to 3 over here, you get a frequency of about 327 megahertz. And so if you want to test between these two models, the best way of doing it, or so it appeared to Govind and company, was that you should build a high sensitivity radio telescope operating at this frequency. And so Govind and his team in 1984 proposed this major new instrument, the Giant Meter Wave Radio Telescope. Govind had actually proposed a giant equatorial radio telescope a few years before, but which couldn't get funding, and there were political problems in Kenya and Indonesia. And so he proposed the Giant Meter Wave Radio Telescope and said, great, let's go build it. And Govind being an intelligent person and his team being superb, Govind designed this telescope. Although the primary science goal was to do redshift to 21 centimeter, Govind designed the telescope to be a versatile telescope, not merely focusing on one frequency and one science area, but he decided to build it to cover a range of frequencies, 150 to 1420 megahertz. And this immediately enabled a wide range of science, not just high redshift 21 centimeter emission. And that is tells you a lot about the thinking of people at that time, and that has had huge implications for radio astronomy in India. So that was the game in the mid 80s. In 1987, the GMRT was approved, funding was approved, and construction started. And the aim was to finish construction by about the late 90s. And Govind and his group didn't rest on their hands. They were building the telescope, but while building the GMRT, Govind and Ravi Subramanian, who was a PhD student in the UTI telescope in those days, started off a search for 21 centimeter emission from galaxies at redshifts of 3.4 with the UTI telescope, which was the big telescope in India at that point. And they didn't see anything, so they placed upper limits on the H1 mass of galaxies. And then in the early 90s, 1991, Juan Uson, Durga Bagri, and Tim Conwell suddenly jumped up and they claimed a very strong 21 centimeter emission signal at a redshift of 3.4 with the very large array, the VLA. And that signal is shown over here from the Uson Bagri Conwell paper. And you can see this kind of fairly clear signal, which is about 10 millijansky bright. And this is almost exactly the kind of signal that you expect from a supermassive galaxy or a cluster of galaxies. Exactly the kind of thing that you predict from a hot dark matter model. And so Jodie Foster got super excited about it and came down to the VLA to also try to confirm the signal. Unfortunately, that wasn't very successful, but they made a movie out of it and they moved on. Kandu Subramanian and Govind wrote a paper shortly after the Uson paper, arguing that, it may not be a single big galaxy. And the reason for that will come in the next slide. Maybe instead of it being a single supermassive galaxy, maybe what's happening is that what you're seeing is a statistical detection of the signal from a collection of small galaxies. And this was a remarkably prescient idea. I'm actually quite amazed that they thought of this. And it seemed like a trivial idea, but as you'll see, it's not trivial. Sadly, Frank Briggs with Arecibo and Claire de Brown with Westerbork searched for the signal, and it wasn't confirmed. And so it turned out to be a completely fake signal arising from standing waves in the VLA waveguides. And so, people basically closed up their instrument. Jodie Foster went back to Hollywood, and we moved on. And the reason that Govind and Kandu and various other people felt that the signal was not likely to be a signature of hot dark matter had to do with the fact that just around this time, by the late 80s and early 90s, people were realizing more and more that hot dark matter didn't quite work. And the early N-body simulations from Davis, Frank, Statue, and White, right to the mid 80s, had started to show that galaxies in these simulations showed more similarities to the real universe when you did the simulations with cold dark matter than with hot dark matter. The structures that you were forming matched the universe in cold dark matter simulations and not in the hot dark matter simulations. And this was not really kind of definitive, but it was indicative. And then came COBE. COBE is the cosmic microwave, the cosmic background explorer, whose aim was to look for cosmic microwave background anisotropies, which were predicted. If you want to form galaxies in the universe, you must have small anisotropies in the microwave background. And these are people who have been searching for these for about 20, 30, 25 years at that point, from the 70s until the 90s, 20 years. Wanu Son spent much of his career searching for these microwave background anisotropies, and people had just not found them. And then COBE went off into space, and they found these anisotropies. And the problem with the COBE anisotropies was that you can link the anisotropy amplitude to the nature of the dark matter. And the amplitude was just way too low in the hot dark matter model to form galaxies at redshifts of 3. And so basically, if the hot dark matter model was right, the only way you could make that consistent with the COBE anisotropies was if galaxies formed by around redshifts of 1. And so people said, okay, fine, that's not possible. We already see galaxies by redshifts of 3, 3.5. Hot dark matter is dead. And by the late 1990s, after Saul Perlmutter, Adam Rees, and Tom Phillips and company came up with this idea of doing supernova 1, type 1a supernovae observations to find evidence for dark energy in the universe, the standard cosmology became the lambda cold dark matter cosmology. So lambda contains about 70% of the energy of the universe. It's dark energy or a cosmological constant. And the remaining 30%, 25% of it is cold dark matter, and about 4-5% of it is baryons. So that was the picture by the end of the 1990s, right when the GMRT started to switch on. And unfortunately, in lambda cold dark matter, as I said, you produce very small galaxies at high redshifts, which means that your 21 centimeter signals are really faint. And that means that there's no chance in hell of detecting these signals with the GMRT, which was designed to detect the signals from hot dark matter models. And so people started talking about building an even bigger radio telescope. And of course, Govind was at the forefront of this. Govind and Peter Wilkinson proposed the square kilometer array under different names in the same IAU symposium in 1991. Because it was clear that no telescope which was planned or being built right then could possibly detect the 21 centimeter emission from cold dark matter in a cold dark matter model. So that was the problem. What do you do? So what you do is that you go and, of course, build your telescope, which is a GMRT. And the GMRT came online in 2002. That's an image of the GMRT. It's got 14 antennas in the central square distributed in a quasi-random way. And it's got the 16 antennas and 3 arms of a Y. And these antennas are 45-meter diameter. And the baseline, the separations between these antennas go from around 75 meters between these antennas, the 3 antennas over here, to about 25 kilometers, between these antennas over here. So it's an interferometer, and you can make images of the sky at these frequencies. And the receivers are very narrow band, the original receivers. They cover 150 megahertz. I haven't listed that over here. They cover 225 to 245 megahertz, 300 to 360, 580 to 660. And this was the wideband system, 980 to 1500 megahertz. In fact, technically, this is 880 to 1500. It was changed to 980 later. Also, the correlator had a relatively small bandwidth, just 33 megahertz. So we could observe only a small part of the band at any given time. And it had 512 channels in its last incarnation. In the original incarnation, it had 128 channels. And this was a fantastic telescope. It had the highest sensitivity of any telescope in the world, any interferometer in the world, these frequencies. The Arecibo telescope, which sadly died last month, has until FAST came along, the Chinese FAST telescope was the biggest telescope in the world and the most sensitive, but Arecibo is a single dish. And so you can't make images of the sky with high resolution. The GMRT is an interferometer, and you can make these wonderful images with the GMRT. So it's got great sensitivity, but unfortunately not high enough sensitivity to take 21 centimeter emission from these small high redshift galaxies that you expect in the lambda cold dark matter cosmology. And so the GMRT proceeded to do really nice work. In fact, the first paper with the GMRT was 21 centimeter absorption from high redshift galaxies. And it did all kinds of stuff on pulsars, on clusters of galaxies, on supernova remnants in the Milky Way, on 21 centimeter absorption, mapping of nearby galaxies, what have you. Did some wonderful work and says a lot about, again, the intelligence of building a versatile telescope. So while all this was going on, the GMRT was built, other things were happening in astronomy. And what was happening was, in a big way, the rise of the stars, so to speak. And this happened because suddenly in the 1990s, a bunch of optical telescopes were built, which completely changed our view of the universe. And the first of these was actually the Hubble Space Telescope, which is not a big telescope, it's only got a diameter of 2.4 meters, the main objective, but it was in space. And this was spectacular. You could produce these amazing high resolution images of galaxies of very, very, very distant galaxies. The second of these was the Keck telescope, the pair of Kecks, if you like, 10.2 meter diameter telescopes at an amazing site, Mauna Kea in Hawaii, at an altitude of about 4,200 meters. And this came online in the early 1990s, 91, 92, just around the time when the HST started operating. And a third of these was the VLT, the Very Large Telescope, on Cerro Paranal in Chile, which is four 8.2 meter diameter telescopes on a site which is about 2.5 to 2,600 meters high, but spectacular site again. So this combination of outstanding telescopes and, almost equally important, new techniques, especially pioneered by Chuck Steidel in the mid to late 90s, early 2000s, allowed you to suddenly observe these large samples of star-forming galaxies at very high redshifts. So until the late 90s, we didn't know too many galaxies at high redshifts. But these techniques really changed our view of the universe. And now we know many thousands, millions of galaxies at redshifts larger than about 2. Many thousands of galaxies for sure. And so what that resulted in was a picture like this, where if you plot the star formation activity of the universe, this is technically the star formation rate density, but think of it as star formation activity as a function of redshift. You can go all the way out to redshifts of 8 today. And what you see is that the star formation activity in the universe basically rises steadily from redshifts of 8 to about a redshift of 3.5. The exact number is not important. And then it plateaus for about a redshift of 3 to about a redshift of 1. And then there's a steep decline from redshifts of 1 to today. So this is the broad pattern of star formation in the universe. And to convert redshift into look-back time, a redshift of 8 corresponds to about 12.9 gigayears ago. So from about 12.9 gigayears ago to about roughly 11 gigayears ago, star formation activity steadily rose in the universe. And then for about 3 billion years, it was about flat. And then in the last 8 billion years, it's declined steeply. This epoch, the epoch from redshifts of about 1 to 3 or 3 to 1, thinking of it in terms of time, is called the epoch of galaxy assembly. And the reason for this is that if you look at the stars in today's universe, half of today's stars are formed at this redshift, redshifts of 1 to 3. And so that's kind of surprising because there's so much star formation happening at this epoch and it declines so steeply afterwards by an order of magnitude. So this is in a log scale. And so this is about the order of magnitude of a decline in star formation activity, redshifts of 1 to about redshifts of 0, today's universe. And so most of the stars you see today, half the stars are formed very early in the universe, on the average about 10 billion years ago. And that's interesting. So star formation in galaxies was about 10 times higher about 8 billion years ago compared to today. So an obvious question is, why did the star formation activity slow down? What happened at a redshift of 1 to cause star formation to switch off? And the obvious corollary to this question is, what's happening with the gas? What's happening to the hydrogen, which is the main fuel for star formation? And so what you really want to do is to measure the atomic gas mass of star-forming galaxies at this epoch, and of course afterwards. And as I said, this is really hard because the 21 centimeter line is weak. And in lambda cold dark matter, these galaxies are relatively small, so therefore you're not likely to be able to measure their hydrogen mass. So how do you get around this problem? The way you get around this problem is that there are two possible ways. One way is that you take a telescope and you observe for a very, 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 very long time. And you hope that your systematic effects, that everything kind of works for you. And you can manage to detect these galaxies. To give you a feeling for this, to detect a typical galaxy at a redshift of 1, you need about 10,000 hours of observations, more than 10,000 hours with the GMRT, which, as I said, is the most sensitive telescope at these frequencies. And so it's really hard to do a 21 centimeter emission measurement of a galaxy at a redshift higher than about 0.25. The highest redshift galaxy that is known today in 21 centimeter emission is at about 0.38. There's a single galaxy there found with the VLA by Jimena Fernandez and collaborators, and we know nothing beyond that. And that's one galaxy. So the way around this is that what if you can combine the signals from multiple galaxies with known redshifts? And this is like philosophically like what Kandu and Govind were saying in 1992. Could you do a statistical detection of the signals? And the idea is basically this. You make an image of the sky, and this is one frequency plane. And there are a number of galaxies at 21 centimeter emission in this plane. And you basically take pieces of the image and around each galaxy, and you stack them together. You simply average them together, aligning them in velocity. So now this is this is the average signal from 10 galaxies, and that's the spectrum that you see. This is the second frequency plane or the second redshift. There's 10 more galaxies here, and this is the average for 20 galaxies. And you keep doing this for different redshifts, and you keep stacking the galaxies after aligning them in velocity. And what you see is that as you add more and more galaxies in, you start building up a signal in the center of the galaxy of this stacked image, and also in the spectral line that you see over here, which is basically taking a cut through this central point. So this is a plot of the emission versus velocity or frequency, and you can see a signal is starting to build up, and you can see that a signal is starting to build up over here. Red over here is bright, blue over here is faint or is negative, and you can see that as you add more and more galaxies, you're starting to see the signals build more and more and more. So what do you need for this to be successful? What you need is a large galaxy sample within the beam of the telescope. You need to be able to observe many galaxies at the same time. That's important. Otherwise, if there are not enough galaxies within your beam, then you can't average these galaxies. The second thing you need is that, remember, you want to stack the 21 centimeter emission. To do that, you need to align the galaxies in positions and redshifts. So you need to have good positions and redshifts from some other observations. And the obvious thing is optical spectroscopy. And the third thing is that you need objects at the right redshift. Right meaning which you can observe with your telescope. And so you need to find a lot of galaxies, a region of the sky with a lot of galaxies with good positions and redshifts and in the right redshifts. And this was done at relatively low redshifts, less than 0.3, by Philip La, Jairam Chegulu and collaborators about 13 years ago. They got a 2.5, 3 sigma detection. And then Apurvo Bera did this nicely with the GMRT last year. And that's great, but that's at relatively low redshifts. What we really want is to push this kind of a measurement where you can detect the emission from this ensemble of galaxies. So over here, you're detecting the emission from 400 galaxies, and that gives you the integrated mass of all these galaxies. Now you divide by 400, or 399 in this case, and that tells you the average H1 mass of these galaxies. And the shape of the line tells you how wide these galaxies are, what their average properties are like. And so this gets, if you can do this at really high redshifts, that would be fantastic. And that was that's the hope, if you like. So we tried this with the GMRT, and it turned out the Keck telescope had done this wonderful survey called the Deep 2 survey, where they gave us positions and redshifts for about 15,000 galaxies at a redshift of 0.75 to 1.4 in 7 regions of the sky. So lots of galaxies, and more importantly, lots of galaxies in contiguous regions, in neighboring regions. So this shows you an example of 2 of the fields of the Deep 2 survey. There are about 1,860 galaxies in this region marked in blue, 1,750 in this region marked in orange, 1,572 in this region marked in green. And what you see as the red circle is the GMRT beam. So all of the galaxies marked in blue are inside the GMRT beam at this frequency and can be observed at the same time. And what is even nicer is that this epoch, redshifts at 0.75 to 1.4, is bang in the epoch that is interesting. Exactly at the end of the epoch of galaxy assembly, covering out from redshifts of 1 to 1.4, and then the epoch where star formation activity starts to decline. So if you can cover this entire redshift range, things would be very interesting. The problem was that the old GMRT could only cover 580 to 660 megahertz, which is somewhere about here in redshift, 1.2 in redshift, and it only had a bandwidth of 32 megahertz, which means that you couldn't cover all these galaxies. You could only cover about 850 galaxies in one setting, 250 galaxies per field typically. So we tried this about 4 years ago. We observed 4 of the deep 2 fields, and we stacked the 21 centimeter emission from about 850 galaxies in 4 regions. And sadly, we got an upper limit on the 21 centimeter signal, and that gave an upper limit of the H1 mass. And you might say boring. It wasn't really boring. It was fun. We got an upper limit, and that meant that we said that the mass was less than some number, which said that these galaxies were not very massive. All very well, but that doesn't kind of really make you feel like going to town. And then the upgraded GMRT came along. So the upgraded GMRT, remember I said that the GMRT has these antennas and 45-meter diameter and so on. That didn't change. What changed was that the old GMRT had narrowband receivers, which covered only about 20 megahertz, 60 megahertz, 80 megahertz, and so on at the different frequencies. And the correlator had a bandwidth of 33 megahertz and 512 channels. The upgraded GMRT, which came online in 2017, had new receivers. This receiver was the same, 980 to 1500, but the remaining 3 receivers were new. And they covered 125 to 250, 250 to 500, and 550 to 850 megahertz. And that meant that you could observe this entire band at one shot with a single receiver. What is even better was that the upgraded GMRT also had a new correlator, and this correlator had a bandwidth of 400 megahertz, which means, and what this meant was that we could observe this entire band at a single shot and observe all the galaxies whose redshifted spectral lines were sitting in this frequency range at one shot. In addition, this correlator, which essentially processes this band, had 16,384 channels, much more powerful than the old correlator. You'll hear a bit more about the GMRT, I think, 3 days from now. But this correlator was more than 10 times more powerful than the old correlator, much more than 10 times. You can see that the bandwidth itself is a factor of more than 10 larger than the old correlator. And of course, it has far, far, far more channels. And this meant suddenly that this problem was much more tractable than it was earlier. And so Aditya Chaudhary led a project to use the upgraded GMRT to observe 5 of these deep 2 sky regions. And he could cover 11,000 galaxies in these regions. And he then stacked 7,500 clean galaxies, which were not affected by interference and so on. And what you saw is exactly or approximately what you saw in the earlier stacked image. You see this red signal over here, which is about a 4.5 sigma signal, essentially the first detection of 21 centimeter emission from the epoch of galaxy assembly. The average redshift of these galaxies is about redshifts of 1. And that's the spectral line that we see, the average spectral line. Let me emphasize that. It's an average spectral line. It's not from one galaxy. It's from 7,653 galaxies. But what was interesting was that this measurement allowed you to infer the average atomic gas mass of these galaxies. And what Aditya found was that the average atomic gas mass, the average H1 mass, can fuel star formation activity for only about 1.5 billion years. For contrast, in the Milky Way, the hydrogen mass is sufficient to fuel star formation activity for about 10 billion years. And so what this says is that the amount of hydrogen in these high redshift galaxies is just not sufficient to fuel the star formation activity. The only way that a galaxy can continue is either to switch off star formation completely, because that will just eat up all the hydrogen. I mean, once you've eaten up all the hydrogen mass, you switch off star formation, or it has to transition into a low star formation activity state. And this basically explains the decline in star formation activity at redshifts less than 1. So now we have a picture for what's going on. We have the first measurements of atomic hydrogen in galaxies at the epoch of galaxy assembly. and we think we understand what's happening in these galaxies. And let me emphasize, this is only possible because of the spectacular, first, the building of the GMRT by Govind and Govind's team, and then by the upgrade of the GMRT. So science is highly driven, experimental or observational science is highly driven by technology. And there are huge connections between what you can do and what is possible to be done, if you like, and, uh, and the instruments that you have. And this experiment was really only feasible because of the upgrade of the GMRT. So where do we go from here? The next steps, of course, now that we've kind of gotten our first bite of the apple, the next step is to really do a detailed characterization of the atomic gas galaxies by even deeper observations. So we're now in the middle of a 500-hour observation. In fact, we just finished the observation. So Aditya is processing the data right now. And he's done 250 hours of analysis already, 11,200 galaxies, and you can see the signal is even more clearly detected. It's about a 5.5 sigma signal over here. And as of a couple of days ago, he managed to finish all of the galaxies, and it's about 7.3 sigma or so. So now you can actually break up the signal into galaxies of different types and look at how different types of galaxies behave in their H1 properties. Super interesting, and something that we will be doing over the next few years. The next thing that Aditya is doing is to push to even higher redshifts. Because remember, we are right now at a redshift of 1, covering 0.75 to 1.4, but the epoch of galaxy assembly goes from 1 to 3. We would love to push to redshifts in the middle of the epoch galaxy assembly, 2 to 3, and we can do that with the UGMRT using the band 3 system, 250 to 500 megahertz. And the observations for this have actually begun about 10 days or so ago. And we'll be doing this over the next couple of years. And of course, finally, what we would love to do is to actually detect individual galaxies via ultra deep UGMRT observations. That is really the next step, or with an expanded GMRT. And that is something we are thinking about seriously now, something called the eGMRT project, expanded GMRT project, where you increase the collecting area of the GMRT by adding new antennas. Or, of course, by building an entirely new telescope, the Square Kilometer Array, which is also being discussed in the international community. So that's where we are today, and that's where we hope to go. So, in summary, then, I hope I've convinced you that 21 centimeter emission studies of galaxies allow you to measure the H1 mass, the atomic gas mass of galaxies, and the velocity field. The downside is that the 21 centimeter line is really weak, and so it's hard to measure this line from high redshift galaxies. The upside, in fact, is that because the line is weak, you can actually measure the mass and the velocity field. So there are, 6 of one and half a dozen of the other. If you want to understand galaxy evolution, you must understand both the stars and the gas. The stars arise from gas, they form from gas, and so gas is the fuel for star formation. If you want to understand how galaxies evolved, you must understand the evolution of both stars and gas. The GMRT was originally designed in the mid 80s to detect 21 centimeter emission from the massive super galaxies expected in hot dark matter. And unfortunately, of course, hot dark matter died a terrible death in the early 90s. Kobe killed it. And standard cosmology today is lambda CDN. And that tells you the galaxies high redshift, the bulk of them have to be much smaller. And so therefore, it's very hard with today's instrumentation to detect individual galaxies at high redshifts. But 21 centimeter stacking allows you to combine the signals from lots of galaxies in your field of view. If your friendly optical astronomers can provide you with redshift for these galaxies, and that lets you measure the average H1 properties of these galaxies, of the sample. And the upgraded GMRT has now given the first detection 21 centimeter emission at these redshifts of about 1. And we find that the hydrogen mass is sufficient to sustain star formation for a relatively small amount of time, only about a gigayear or so, very different from the local universe. And this kind of explains the decline in star formation activity at redshifts less than 1. The next steps, of course, are to carry out a detailed characterization of galaxies at redshifts of about 1, and then to push to even higher redshifts of about 3 or so. And that's what we're trying to do right now over the next couple of years. And finally, of course, maybe the next 5 years or so, we really want to detect individual galaxies and characterize individual galaxies with ultra deep GMRT runs, GMRT observing runs, and finally, either the EGMRT or the Spare Kilometer Array. So I'll leave it there then. Thank you very much.
Sir, why don't we use linear regression models to predict a mass of higher redshift, higher and lower redshifts?
What do you
Like
mean?
the machine
What do you mean by
learning model,
linear regression models?
the machine learning model, which like we have the initial data with us.
You have
So
initial
we,
data in the local universe. You can't
yeah,
use
so
that to, so any model that you have is only good as far as you have a measurement. You can predict stuff, but how do you demonstrate that that is the mass?
like we can just theoretically prove that for this amount of redshift, it will have a particular amount of mass.
No, you can't. You can't prove it, first of all. Theoretically, you can't prove an observational thing. But more importantly, that only works if you have a theoretical model which understands everything. Baryonic physics is very complicated, and we do not have even remotely a good theoretical model to explain the evolution of galaxies. So it's almost the opposite. It's not you won't do a linear regression model. What you actually do is that you try to build galaxies using gravitational clustering simulations.
Okay.
And so you start with a cosmology, you evolve galaxies in this cosmology, and then you seed them with baryons. The problem is that baryonic processes are not very well understood, and the processes are extremely complicated. So you have to do things like cooling. You have to do things like how do supernovae go off, and how do they blow gas out? How do metals mix with the gas? All of these things are really complicated processes, and you cannot model them easily. So, in fact, the way in which you do these models is that when you do these simulations, you actually use observations to constrain the simulations. And one of the things that we don't have today is observations at high redshifts.
Thank you, sir.
Pranav is asking one question on chat box. There is a research study carried by a Chinese team, I guess, which have found a galaxy at redshift 11. Any comment on that?
Well, kind of, yeah. People are skeptical. So there's up and downs. Uh, the problem with finding galaxies at redshifts of 10 or so is that you need to worry about, I mean, the way you find them. So how do you identify the redshift of a galaxy? The way you identify a redshift of a galaxy is that you need a spectral line. But a single line does not give you a definitive redshift, because if you see a single line, you need to know which line is it. And that's the problem. So what the Chinese team has is a single line in this galaxy, and that could be either Lyman alpha emission, in which case the redshift is very high, or it could be, for example, oxygen emission, in which case the redshift could be 2 or 3. And that has been the huge issue with determining galaxy redshifts at redshifts of about 10 or so. You can only see Lyman alpha usually in these galaxies. So all this will change in the next year or so once the James Webb Space Telescope gets launched, because then we can actually see these individual galaxies in their optical lines. So JWST will cover all the way up to about 50 microns, and so you can actually go out and observe these lines and observe the optical lines redshifted into the JWST bands. And so that will change things. Right now, there's a lot of skepticism about this Redshift 11 galaxy in the community. People don't really believe it because the evidence is not very strong. The shape of the line does not look like Lyman alpha right now. And there are other properties which make the galaxy unlikely to be Redshift 11. I'm agnostic about it as of now, but the community is certainly the optical community is skeptical. Okay, great. Yeah, thanks, Prakash.
Yeah, so to all participants, so be present at 2 p.m. So we are going to discuss about the experiments.
Nisim, can I ask you a side question?
Yeah, of course, Desh.
Yeah. After having stacked the